Okay, rate. You've dealt with the concept of rate all the way back to Algebra 1. It's not a new idea. Let's look at one of your first encounters with this is probably the equation distance equals rate times time. And if distance is given in miles and time is given in hours, the rate in this context would be a speed in miles per hour. So in this context, your rate is a speed. Let's solve this for r, and notice r is d over t. And so when you say miles per hour, it's literally miles divided by hours. How many miles, how many hours did it take to do that? It doesn't have to be a distance, rate, and time situation. Say that you have a hose running into a swimming pool. You're going to fill a certain volume of water in a certain amount of time. And the rate there is the rate of flow in, for instance, gallons per minute, gallons per hour, something like that. Okay? And so if I solve for R again, it would come out in volume over time. So this might be gallons, for instance, per hour. Okay? Now, what does this look like when we do it graphically? If I take distance, just to take this first example, compared to time, we've dealt with problems like this. Like, say, going from point A to point B. Look at the slope here. Notice that the rise over the run, in this case, the rise is the difference between two distance units. So this has the units of distance. And the run is along the time scale. So this difference has units of time. And so if I take the rise over the run, I have d over t, which is back to this miles per hour thing. So your slope is equal to your rate. Okay. And so we're very familiar with finding slopes of straight lines. What about when we get into more realistic problems where we don't have a trip that involves a constant speed the entire way? It's much more likely that when you take a trip, you're going to speed up and slow down and stop, maybe even go backwards and so forth. And so what if you have a distance versus time graph? It looks something like this. And you want to say, how fast am I going at different times? Well, just by looking at the graph, you can see that where the curve is steep, you can say I'm going fast in the positive direction here. Where the graph is essentially horizontal, you can say, well, it looks like I'm motionless at that point. And over here, it looks like we're actually going backwards here. And so for any one point on this graph, intuitively you can say there's a certain speed associated with each point. But there's a problem. When you compute the slope, you use 2 points, not just one. So to say, what is my speed at a particular time, we're looking for something called instantaneous rate. And the question comes down, how am I going to compute that? Because I need 2 points to calculate a slope. Okay? So that's the problem we're going to be attacking here. Let's look at the problem that was posed by the textbook in this section. Okay, the problem shown in the text was a door, it was an automatic door opener. This is the kind of thing you find in public buildings where you have to push a button and the door opens, like if you have a wheelchair access issue and you don't want to require the person in a wheelchair have to use one of their hands to hold the door open while they're trying to maneuver their wheelchair through here. So by pushing the button, the door starts by swinging open. And notice that since it's steep here, it looks like it's swinging open quickly. It gets to maximum maximum degree of openness, and it sort of hovers near that point for a period of time. And then it's coming with a negative slope, which indicates that it's closing again. And the speed changes. It gets slower and slower until it's right near the closing point, and then it slams shut and latches again. Okay, so we can see that we have the opening and closing of the door varies as time goes on. So we want to ask, what is the rate at any point along this curve? Okay, what's the rate at any time? If I say at 1 second, how fast is it opening? I can see how far open it is by evaluating the function. I can plug in 1 second here and it'll give me how open it is. But what about how fast is it opening at that instant? Okay, so for instantaneous rates, we have to figure out a way to apply the concept of a slope, which needs 2 points, and apply that to a situation where we really only have access to 1 point. Let's look at this problem in GeoGebra and see if we can use some of the tools we already have to at least try to approach this problem and explore how we might get at that. Okay, here we're using GeoGebra. If you took pre-calculus from my courses, you've already had a lot of exposure to GeoGebra. If not, then you need to get familiar with it. This is my alternative to using a graphing calculator. I think graphing calculators, they have tiny screens and keyboards and so forth. Here you have a full computer keyboard and a lot more to work with. Over here we have an algebra view, so as I put something here geometrically, I can also see what it looks like algebraically. In this case, I actually entered it algebraically and then it graphed it automatically over here. By the way, I can input it right down here at the bottom, but if I typed in this function as shown, it wouldn't have had an automatic start and stop point. It would have just kept on going to infinity here, or at least way out. Okay. And so in order to get a function with a domain that's been restricted, let's double click on this and it shows you what we actually typed in. If you type in the word function and use square brackets, then you can put in the definition of the function followed by 0, 7, and that restricts the domain to horizontal axis numbers from 0 to 7. Okay, so that's how we got this thing in here. I typed it out of the book, I changed the t to an x, and I put in the domain that way. Alright, now back to the problem. What if I want to know the speed of opening of the door at 1 second? Alright, so let's put in a point on the curve at the 1 second point here. So come down here, I'm going to call this point A, and say A equals, and parenthesis 1 for the time. And since the function already has a name, it's d of x, I can say d of 1. So that will give me the function value at 1. And there we are. There's A. And let's just move the letter over there. Okay. Now what I'd like to know is how fast is this door opening at that point. If I look over here, I can see that the point is 1, 100, which tells us that at 1 second it's 100 degrees open. But we don't want to just know how wide it is, we want to know how fast it's moving at that point. Okay, so how would you do that? Well, the only way we know to find the slope of the curve is to find 2 points and take the rise over the run between those points. So one approach would be to approximate. So let's define a point B, let's call it B1 since we're going to do this several times, equals, let's go 1.1 and then D of 1.1. Alright, so here's a point that's very nearby, and the question is, what is the slope between these 2 points? Okay. Notice the equation of the line given here is something x plus something y equals something. That's in standard notation. If I put it down here in y equals mx plus b form, I can read the slope right off of it. So y equals something times x plus a constant. And so it looks like the slope is 26.336. Okay. So, is that the slope at A? Well, if I zoom in, notice that it's pretty clear that this line that I drew crosses the curve at that point. It's not right along the curve, so this is not quite steep enough. So the actual slope at A, this is an approximation that might be a reasonable approximation for some purposes, but it doesn't really qualify as saying that is the instantaneous opening speed of the door at this point. So let's try just bringing this point in closer, see what it looks like if we get a better approximation. So let's say B2, and let's let that be, this time let's say 1.01 and D of 1.01. Okay, so that's like 10 times closer, isn't it? All right, here, let's center it up a little bit. Okay, so let's put a line from A to B2, and notice that that is definitely steeper than the original. If I put this equation over into slope-intercept form, now we have that the slope is 30.23. Previously it's at 26.33, so that's quite a difference. So getting very close is important when there's a lot of curvature here. Well, if I zoom in some more, notice that there's still some separation between this line and the curve. It's getting pretty close, but say that we want to have better accuracy than that. What we really want to do is, I'd like to know what is the speed of opening at this point itself. That's what we're really trying to get at. So let's do at least this one more approximation. So let's let B3 equal, parentheses, 1.001 D of 1.001. Okay, and so notice this is, compared to B2, this is 10 times closer again. And if I connect A to B3, okay, this again looks like it's a much better approximation. It's still going to be an approximation because I'm not really coming all the way down to A, I'm coming only this far. But what is my slope? Let's change this into slope-intercept form. 30.64. Well, this was 30.23. This still says 30, so it looks like 30 is a pretty good approximation, but that's an underestimate. How high will it go? Well, we're not there yet, so it's going to be something greater than 30.64. Will it get as high as 30.7? Well, we'd have to keep on doing this over and over to get an answer there. Okay, let's try something a little different. Let's back off so I can get a point here. Let's go and put a point here on the curve, and let's make it a different color, something we can recognize, like hot pink, for instance. All right, and let's take a line connecting point A to B, and let's make that again the same color. All right, now as I slide this point, let's look at what's happening. Let's notice that E is the line, put it in slope-intercept form, and let's bring this down close, and let's zoom in. Okay, so here is just past B2, here it just passed B3, so now we're closer to A than B3. All right, notice it says 30.658, this was 6.4. If I come down closer, here's 30.67. So why mess around? Why not go all the way to A? Let's try that. So if I go all the way to A, will I get better accuracy? Well, look what happened. We lost it. As long as this is a separate point, we had values here, and the closer we get, the more accurate it was. But then if I go all the way to A, it just goes away entirely. It just becomes undefined. And why is that? Well, the reason you're having a problem is you can't define a line with just one point. And if A and B are the same point, any line that goes through A is also going to go through B since they're the same. And so you have no discrimination between which lines work and which lines don't. So we don't have a particular line anymore. And so what we're restricted to find the slope at A is not the slope of the curve at A, but the slope of an average over an interval for points near A. Okay, now that might be good enough for some applications, but it doesn't really, in principle, answer the question we're looking for is what is the actual rate at this point. Okay, so let's look at the process again. What we're doing is taking a sequence of approximate values. Way back here we have B1, here's B2, here's B3, and then this slider we can just represent as, just to try and see what's going to happen in general as we go to B4, B5, B6, and so forth. As we get closer and closer without actually going to A itself, we're approaching some number. The number looks like 30.6 something, greater than 30.66. I think we got around 30.68 at one point. It was 30.67. Okay, so we can tell approximately what it is by doing this a few times graphically, but what we mean, if you want to say what's the concept of instantaneous rate, the only way we can get at it appears to be by successive approximation. And so we can say the instantaneous rate at a single point is the limit. It's that number, that this sequence of numbers here, these slopes, no one of these slopes is the slope at A, or the rate at A. These slopes form a sequence that point toward a number. The number that these are pointing toward is the limit, and the limit is the number that we really want. Let's go back for a second. So, what do we mean by the rate at a point? The rate at a point is found by taking the slopes between this point and nearby points, and as the nearby points get closer and closer without becoming the point itself, the number that this sequence of slopes approaches is the slope at that particular point. Now if we go back and we talk about the concept of an instantaneous rate, the instantaneous rate is not a slope in the conventional sense. We have another name for it. It's the limit of this sequence of slopes. And the name we have for it is called the derivative. And that's one of the big topics we're going to encounter in calculus, is finding the derivatives for various kinds of curves. But the process, the concept, this is the concept of instantaneous rate. The concept is we're going to take a sequence of approximate values by taking slopes over smaller and smaller intervals, and see if we can use that process to see where these numbers approach. So for this point in the course, all we're looking at is to understand the problem. The problem of finding an instantaneous rate is you can't find a slope with just one point. So we fall back to finding the slopes between pairs of points, and we let the pairs of points become a sequence. The number that these slopes approach or point toward is the number we want, and we call that the derivative of this function at that point. Okay? There is our overview. Let's look at the first couple problems, and exploring those, try to get a handle on the concept. We're going to spend a lot of time in this course finding derivatives, but for now, how do we understand what a derivative really is? Okay, try the problems.